Okay, today's lesson is for October 12th, 2011, Wednesday. We're going to begin a new section on forces by conducting a demonstration with a tug-of-war rope outside. Two people will demonstrate using that tug-of-war rope, and we're going to record the demonstration with a camera to show in class when we come back in. It's going to be really important that you take a pen and paper outside. That way you can write down any observations about the tug-of-war rope demonstration. That way you can participate in the discussion when we come back in. Okay, at this point we should have already finished discussing the tug-of-war rope demonstration in class. We're going to go ahead and begin reviewing some notes in PowerPoint. Do not forget that you can access these notes on our weekly agenda in PDF format right over here by clicking on this link. You're also going to be given a copy of the notes with missing blanks as you walk into class in a handout form. Make sure that you follow along as I give this lecture and input any missing information on your handout. And again, you can also access this YouTube video of the lesson here at the link on your weekly agenda. So let's go ahead and take a look at this PowerPoint. Okay, so it's going to be about force and motion. So force is basically a measurement we apply in physics to describe a push or pull that causes an object to move. There are many different types of forces that can actually affect our motion. For example, we've already discussed with free fall that gravity accelerates all objects on Earth to the ground at negative 9.8 meters per second squared. The fact that we have an acceleration of negative 9.8 meters per second squared tells us that the velocity is changing, so there has to be a force on all objects that are falling here on Earth. So again, as I explain these things, you should be inputting them in your handout. Okay, so let's start up here at the top. For force, the unit for force is a Newton, and we're going to be using capital N to show that unit whenever we write a number. So you might see a number like 10 newtons, and you would just have a capital N at the end of that. The Newton is actually equal to a kilogram times meters per second squared. These are equivalent units. The obvious good thing about a Newton is that it's abbreviated, so we don't have to write kg times ms squared. We can just write the capital N. The other thing about force is that it is a vector quantity, so whenever we put a positive or negative value in front of that force value, or the actual magnitude, the number, we're going to be actually telling the direction for that force. And I've written down the general directions that are kind of a rule of thumb for whenever you see a force value. Positive forces are generally forces that go to the right or that go up. So if we have some object, I'm going to go ahead and draw an object here. We had an object. A positive force would be one that either went to the right or one that went up. For negative forces, these are going to be forces that go to the left or that go down. And if you think about it, if we were looking at a coordinate plane in math, you know, where you have an x and y axis, these would both be positive portions of that line, number line, and these would both be negative. So it kind of makes sense that bottom and that left and down are negative and right and up are positive. Okay, so the sum of all forces acting on an object is basically going to be the definition for net force. Whenever you have multiple forces, you're going to actually add them all up, and we're going to make sure we put the negative for forces that go left and down and positive for forces that go right and up. And when we add all those forces up in the x direction going across and the y direction, we can actually calculate the net force of the object. And that's where this equation down here comes from. Basically says that the net force is equal to the summation of all the forces. This little E symbol, this little E looking symbol here, stands for the summation of forces. So you'll see here that I have F1 plus F2 plus F3 plus ... So basically we're going to add up every force that's acting on the object and that X line, and then also on the Y, the vertical. Alright, so Sir Isaac Newton was an English physicist and mathematician. He explained the three laws of motion in a book he published in 1687. We're going to be discussing these laws in detail over the next week. The first law of motion is sometimes called the law of inertia, so sometimes this first law of motion will be referred to as the law of inertia. It basically states that objects in motion will remain in motion unless an unbalanced force acts upon them, and objects at rest will remain at rest unless an unbalanced force acts upon them. This should actually be kind of intuitive. When an object is just sitting there, to make it accelerate or change its velocity, we actually have to give it a push or a pull, so we have to apply a force. Likewise, if we had an object moving a certain constant speed, to change that speed we would have to apply a force to slow it down or to speed it up. You can think of an example where you'd maybe be in your car going on cruise control at a constant speed. To actually change your speed, you'd have to hit the gas pedal or you'd have to hit the brake. So to take a look at the question and try to answer it, it says, if this law is true, then why would your car eventually come to a stop if you release the accelerator and just coast? So if you were to take it off of cruise control, most of you should notice that your car would slowly come to a stop. So take some time and think about why that might be. Okay, so hopefully you've gotten the answer by now. The answer is friction and air resistance. The car actually, as it moves, there's friction with the road and other moving parts in the car that oppose the motion of the car forward. So that could be an opposing force that causes a negative deceleration of the car. And there's also the air resistance against the car's motion. Okay, so if we kind of take a look at this and we draw a little circle here to represent this car, the car is going a certain, when we're actually pushing the gas pedal, it has a certain force that's being applied by the gas pedal. And you have a certain amount of air resistance, and you have a certain amount of, so I'll put air right here. And you also have a certain amount of force that's attributed to the friction, like I said, for other things in the car. Now, when you're pushing on the accelerator, when you have it in cruise control, these forces will be equal to each other, and so the car will maintain its speed. But in this example, when you take away this force that we're applying with the accelerator, all that you're left with is a force for the air resistance and a force for the friction. So we'll go ahead and write those in. So when you only have forces opposing the motion of your car, then that's going to mean that your car is actually going to slow down because the acceleration is in this direction, negative to where you're going. Okay, here we're going to go ahead and match the situation with the direction of the net force on that object. So in this first situation, a car moving to the right slows down. The net force would be in which direction? Right here, a car moving to the right is actually slowing down. It should actually be left because the force against the car's motion is greater going left than the force going right with the motion of the car. So for you can go ahead and draw a little line here going to left. Next, a car moving to the right speeds up. So a car moving to the right speeds up. So in this case, the net force is to the right because the force going to the right is greater than the friction air resistance forces against the car's motion. We know this is true because the car has an acceleration to the right. It's actually getting faster. So we know that the net force is actually going to be going in that right direction. Okay, I want you to go ahead and finish the remaining situations on your own and raise your hand if you have any questions. All right, unbalanced forces cause the acceleration and net force in one direction. When all the forces are balanced, the object is in equilibrium and should have a constant velocity. For this example, the forces on the book on the y-axis going up and down are in equilibrium, and you can actually see that right here in this diagram. So we've got the book acting as our system, and then we've got a force from the table on the book and a force from Earth acting on the book. This is basically the force of gravity. Sometimes you'll see this, instead of being like that, it might show it as F little g, force of gravity. So we actually have these two forces equaling each other, and it makes sense because gravity is pushing down on this book, but for this book to have zero acceleration, to stay still, on the table has to push up with the same amount of force against gravity. Now, if this table wasn't strong enough to push up with that same amount of force, obviously it would break and the book would continue to move downwards until it hit the ground. So that's in the y direction. Going up and down, our forces are in equilibrium. There are unbalanced forces, however, on the x-axis pushing the book to the right. So here you have the force of your hand. You'll see the person pushing on it, and their velocity is increasing, so we know we have an acceleration. And that acceleration means that we have a force here that's moving the book forward. The issue here, and we're not going to discuss it in this problem because I haven't shown it, but there probably is a little bit of friction between the book and the table that would be going against there. And we would actually see some problems where they say take into account friction. Well, then you'd have to draw a force for friction going back in this direction. Okay, a free body diagram is a depiction of the forces acting on an object. The forces are shown as vectors that branch off of a dot that represents the object. Okay, so it's basically a pictorial model of all the forces that are kind of branching off of your object. There's some rules that you have to follow. You need to represent the object with a dot, so I'll kind of show an example of one here. Represent it with a dot. And we'll use that book on the table, for example. You need to represent each force with an arrow pointing in the direction that the force is applied. Again, these are vector quantities, so you have to show a direction. So for the force of a book on a table, you would have, remember I said there's a force that goes up against gravity, an equal amount. So let's just say this book's just sitting there. This would be the force of gravity, and this would be the force of the table on the book. So they're going to be equal. That means that this book is sitting in the same position. Which brings us to the next thing. It says arrows should be proportional to the size of the force. So here I've shown these arrows to be pretty much equal. They're not exact because I did it freehand, but they are pretty much close to equal. And so they should be proportional to the size of them. That way people can see if the net force is down or up. If this force were greater than the top force, that would tell me that there was a net force down, and so this object was probably accelerating downwards. You're also going to want to make sure that you label each force with an appropriate subscript letter that describes it. So F subscript G is going to be equal to the force of gravity. We could do F subscript A for like the force of air resistance if we wanted to. You're also going to choose a positive direction and label it on the force body diagram. So for us, like I said, we're going to use the top going up and to the right as positive directions. So we would just write, you know, y is positive up here. Okay, so we'd write that up there. So we know that if we're going up, that's a positive value for a force, and down would be negative. Okay, so those are some of the main directions for that. Here are a couple of examples. So you can see here you've got a person's hand actually holding up a ball. So you have the force of hand on the ball. Then you've got the force of gravity, the Earth's mass on the ball, pushing it down. These are equal, and they've shown you that the positive direction is up. So they showed you a little arrow with the positive value for y. Just so that you know that this is a positive force, and this would be considered a negative force if you were trying to add them up for the net force. And again, if we wanted to just draw a quick example of calculating the net force for this, it would just be F net is equal to, and again, this is positive, so it would be the force of the hand on ball. And then we're going to subtract, because it's a negative value for force, the force of Earth's mass on ball. Again, I like to show this as F little g just because it's a little bit easier for me to remember. In this second example, you've actually got a string holding the ball up. So the contact is coming from the string, not from your hand. But you'll notice in this case that we still show the force of the rope going up and the force of Earth's mass on that ball going down. Okay, so even though you're pulling it here, we're not going to show that force down there pushing up. We're going to show it on the top. Alright, so what I'd like for you guys to do with the remainder of class time is do a really good job of depicting whatever forces you think would be acting on the systems that I've described in these 5 situations. And if you have any questions, please make sure you ask. we're not going to have any homework for this evening unless you haven't finished your previous lab from yesterday. And that's the end of this lesson.